about that.
But there it is. It's on Discord. I'll get started now. Thanks so much for staying. I know 2 hours is a lot of time to kind of give us, but super appreciate it. And hopefully this is interesting. I will say that like this is um, definitely one of like given the title of like this week being a theory lab, it definitely falls into theory. It's not like something that like we can go break passwords with today or tomorrow, but it is interesting. And the subject is conjugate coding. To me, from the very limited perspective that I have, this seems to be kind of the birth of quantum information. Um, it started with well, before we get into who it started with, I think like we can talk first about like the underlying principles that allow us to think um, in this manner and kind of justify this algorithm. Um, so like superposition. Thanks that I don't have to spend an hour covering that, Will, because you got that. But like if anyone is new or joined, as briefly as I can, superposition refers to the ability of, under quantum mechanical laws, representing states not as definitive singular values, but instead as a composition of singular or non-singular values. And so this allows us to um, have states represented in a a very much more probabilistic manner than with kind of binary representation of states. Um, so another fundamental will be we need to figure out how polarization of light works because we're going to use this. And then like we didn't talk about it in the superposition lecture lab, but like measurement is also something, I mean, we talked briefly, but measurement is something we need to kind of dive deeper into for the purpose of like figuring out what is conjugate coding and like and why conjugate coding. Um, so I'm not a physics major. I do computer science. Terrible at physics, but I'll give you this like simplified perspective. So like we have light that can be emitted or propagated along some like space, right? And some type transverse waves specifically, which are what most of the like visible light is, contain the property of polarization. And so like it spoke very briefly in that Kurzgesagt video about polarization representing superposition. But what we can see here is that like we have one wave that propagates along the axis of direction that this light or this photon is moving, right? But then we have another wave or field, the magnetic field, that actually oscillates perpendicular to this like forward propagation, right? So like if we think about like a guitar string, well, you can pluck that guitar string, and depending on how you pluck it, it's going to vibrate maybe like either up and down or side to side, right? Well, light does this, except it does both of them at the same time. And like this polarization allows for us to represent actual quantum states and systems physically within a photon. And we also have tools that can kind of do this depolarization and break down into either a magnetic or an electric field. But the kind of like interesting point is that we can't measure both the electrical and the magnetic field at the same time with true precision. The more you learn about the electric field, the less you know about the magnetic field. Heisenberg's uncertainty principle, not something for today, but something for down the line. The main like gist of what I want to get across is that like we talked about superposition very abstractly in the previous lab, but like this is something that like if we want to make computers, we need to represent this like physically, and photon representation is one way to do this. So like we can then like look at this little expression right here, and we would say that this quantum state represented by phi is equal to cosine theta horizontal plus sine theta vertical. And so like gibberish, right? But essentially we have like these think back to the ones and zeros from the last lab. So the kind of like implied thing is that we can either get like 0, 0, we can get 0, 1, we can get 1, 1, etc. But the more interesting part is the probability of actually measuring each, right? And so this h value represents horizontal. And so like this quantum system consists of two things. It consists of this like horizontal propagation and then this vertical propagation, right? Oh, I did that wrong. Horizontal and then vertical propagation. But like we tie onto that probabilities because again, like in quantum systems, the interesting thing is not like the values, but it's the probabilities of measuring certain values. Because with that, we can make like complex superposed systems and like do funny things to them, right? And so we have cosine theta horizontal plus sine theta vertical, meaning we've got these two possible states, horizontal and vertical, and then we are attaching to them the probabilities for each. And so like cosine is just sine shifted over one phase, right? And so like at times the cosine is like 100, then sine is 0, or like roughly speaking. This probability for each then implies on theta. And so with theta, we are actually able to like define the probability of measuring horizontal or of measuring vertical if we ever depolarize this, right? If we ever measured it. Any questions? That was maybe weird. If not, then we'll go on to the next thing. So like we talk a little about putting or at least being able to represent physically a quantum state, but now we need to think about like measuring a quantum state. And we briefly talked about this earlier, but I want to kind of like hammer this back in. You don't get to retain information after you measure a quantum system. So like you can kind of find quantum systems out there in the natural world, and you can like watch electrons being kind of transmitted between atoms, and you can do things to that, and then you can maybe measure the atoms and you'll only see one electron at the end, right? Like in the double slit experiment. The notion extends towards polarization in light. And so if we have this singular photon that is propagating along with a vertical and a horizontal component, we could then use a bifurcation device, a bifringement crystal, I believe they're called, which can allow us to tear this apart and say, hey, what was it? Was it horizontal or was it vertical? Because up until that measurement, we had horizontal and vertical, right? We had them represented, in fact, by this cosine theta h plus sine theta v. But this is the quantum system, and we only get to talk about a quantum system until it's measured. And so at this point of measurement, what's depicted here is that we have this quantum state, right? This phi that is represented by cosine theta horizontal, the horizontal component, plus sine theta vertical component. Now, putting it through this little box, this little beam splitter, what would happen is we would have to actually observe with probability sine squared theta the value of a vertical beam, or like the vertical component. So like we would, upon measuring this, we would only either get an electric or a magnetic field, and say like vertical is the electric field. Well, we have sine squared theta probability of getting this electric field, and that's given to us by this notation right here. So like we talked about how this is the probability, right? This cosine theta and the sine theta. That's just the probability for this state. So like H and V are the possible states. These are those corresponding probabilities. Except like they're not the corresponding probabilities. They're the corresponding probability amplitudes, which means that these can be negative or positive. And so like if you see here, if this is our this is our sine wave, and then this is the red is our cosine wave, they don't just go from 0 to 1 to 0 to 1. They go to -1 to 1 to -1 to 1, right? And so we don't actually have just the probabilities depicted here. We have like probability amplitudes, which like correspond to negative values sometimes. And like, how would we even like measure or like think about negative probabilities? Like, what does that mean? That's like gibberish. So we have to actually take the absolute value of that and square it. The inner product of the state and the state in its entirety and that singular state, so like horizontal and vertical, times the horizontal component, the absolute value of that squared. This bracket right here is just denoting that there's an inner product going on. Not super important. Like this math, we're going to work with it like plenty more times. So like, don't get scared if you don't get this, because I didn't get it the first time.
Yeah. And then that idea of kind of combining and then squaring, taking the absolute value and squaring quantum states, that is a common way of collapsing a probability density function into a singular bit. Just wanted to put that out there.
Yeah, absolutely. And so like we solve for the probabilities here, right? And then it gets to the point where like we get to measure either electric field or magnetic field, either vertical or horizontal component. And so like we have come to this point where like we know how to put things into superposition, right? We can just grab a light polarizer and we can polarize and send photons, and then we know how to take them out of polarization, right? And this like polarization is a stand-in for superposition, is what it is. And so like we only get to measure either horizontal or vertical, right? Or up dag, down diag for diagonal, which if you can just imagine shifting this cube 45 degrees, well then we would get a 45 degree kind of beam right here, and then a -45 down here. That is just like a different way to split the components, but it's very much similar. The probability amplitudes change a bit, but it's simple. It's similar. But something to note is that the probability amplitudes don't stay the same. There are changes, but it's the same concept. It's the same kind of idea of pulling something out of superposition. Something that's like fundamental to this is the no cloning theorem, which I am not going to present a proof for because like we should do that at another lab. But essentially this kind of gives us the idea that you cannot copy a quantum state, because copying equals measuring. That's like it boils down to just being as simple as that. But like, of course, you can't just take everything that that scientists say as like objective truth. And so there's a proof to go along with that, and we'll look into that another time. But for the sake of this argument, let's just assume that we can't just clone this and then go measure it some way else. You know, you only get to measure it once, and copying is measuring. So this dude right here in the really cool straw hat, that's Stephen Weisner. He developed conjugate coding in the late 1960s. Don't have an exact date for it because he was actually rejected from publication. Many people say it's because it was just like way too ahead of his time or of its time. And I thought that was just like cool to note, because we have a research kind of endeavor going on within QCC, and some of you might like take that up. And research is really hard, and a lot of times like getting denied from publication isn't to say that like your contribution wasn't important. I mean, like the people that are reviewing these papers are also humans, and so I mean, conjugate coding has not like turned into anything. Well, it hasn't like by itself like changed the world, but it's certainly like it's worth us talking about, and it's just a very important theory that like later got published.
Yeah.
But his goal was, I want to send two messages, but I don't want the receiver to be able to read both of them. The receiver can only read one of the messages, but not both. And so, like, practical application of this, you might rack your brain for one, but the kind of premise that it proposes can be extended to other applications that we can talk about, that like are a little more interesting.
Yeah, but in terms of a lot of stuff about the quantum internet has been going around. Very important for the quantum internet because with quantum encryption, using conjugate coding, you can essentially communicate with another person. Um, you can send messages to another people, and you can tell when somebody has intercepted that message because of the measurement of the quantum state. So it's like a red flag that when when the polarization happens, you can tell that the quantum state's been collapsed. So oh, somebody's read my message. I just thought that was really cool, using quantum mechanics as a signal that your message has been intercepted. So think about governments using that for spying on each other when sending messages to each other. You could tell when a spy has intercepted your message and read it. Just thought that was cool.
Yeah, absolutely. And just like something to point out, it's actually upon depolarization, not on polarization, because depolarization is the measurement.
My bad. Yeah, I did say that wrong.
You're good. Yeah. So awesome. That sounds like a hefty goal. How can we actually implement this? So there's two parts to this, right? Like, we have a sender and a receiver. And so, like, the first part of this is like, okay, how do we send this message? Well, we need a few things. We need a light polarizer for one. We need to grab two messages that we want to send, right? And we want to convert them to bit streams. This is like just as simple as finding an encoding, and like converting those like whatever UTF characters or ASCII characters into ones and zeros, right? And so, like, one thing to highlight is you have two messages that you're going to send, right? But only one of them is going to actually get read. And next we have to find a medium for transporting this message.
And just real quick, Ted, do you mind if I interrupt?
Yeah, go for it.
Just want to clarify the bit streams, just in case anybody is like physics perspective or math perspective. It's like, think about the message "Happy Birthday" broken down into ones and zeros. That's what you're creating two copies of that, and each letter in the alphabet is represented by a string of ones and zeros. So you would convert like "Happy Birthday" into two messages via ones and zeros. Exact same copies. Just want to clarify that, Teddy. Sorry.
Yeah, you're good. You're good. So, so then we grab something like a fiber optic cable that can send photons, right? But like we actually want to be very particular about this. We want to send one photon at a time. And this photon, we have a light polarizer, so we're going to polarize it because we want to put it into superposition, right? Because like this is a quantum application. This isn't classical. And so the next part of this is, so for like the ith bit of this like transmitted message, you've got two messages and you're going to kind of put them all together in one message, right? But for every position of your composed message, you're going to flip a coin or use some random generator. And depending on if this coin is heads, well, then you are going to grab the ith bit from or grab the next bit from the first message, right? If it's tails, you grab the next bit from the second message. And if this is from the first message, then you would polarize it 45, negative 45, which would just be like upper diagonal, lower diagonal, right? And so like this is akin to changing the way that we're using this this polarizer. We're shifting it or rotating it by 45 degrees, thus changing this sine squared theta and this cosine squared theta. They will be something different. So we have this idea of like, we're going to go through all the coins, all the messages, right? Or all the bits from both messages. We're going to flip a coin to decide which one we put first, right? So like this process of like flip a coin, okay, message one, flip a coin, okay, message two. the idea is that like this is seemingly random, and so like we have now created an output message that is the length of the sum of the message one and message two, but the ordering is somewhat random. So like if this is if it is the first message that's chosen, we polarize it 45 negative 45, otherwise 0 90. And so like what this just means in plain English is that we're setting this theta value. So this like the theta value is determining the probability of measuring in either state or basis, right? When I say basis, I haven't used that word, but that just means like horizontal and vertical are the basis for this up down or this horizontal vertical, whereas 45 negative 45 are the basis for the diagonally shifted depolarizer. So this kind of like illustrates how it is that we do that, right? So like for the ith random bit, the ith like coin flip, if we get like tails, then it's 0, right? And then if it is of the first sequence, I'm sorry, so like this was wrong. So this polarization doesn't take place because of like being message one or message two. It takes place based on the value of message one or message two. So like that's probably gibberish, but like if we go back to like we flip a coin, right? We flip a coin and then it tells us, okay, grab from message one or grab from message two. That's the function of the coin. It tells you where to go. But then based on like you already know where to go, you already know that you're doing message one. Well, you look at the value for that that next bit that you're gonna like write out. If the value is 1, then you polarize it 45 negative 45. Otherwise, you polarize it. You polarize it to 45 or you polarize to negative 45. Otherwise, you polarize to 0 or you polarize to 90. So what we're doing, like we talked about it earlier with like the probability that Will showed or of that like 4-valued vector was 0 1 0 0. So that meant that for the second bit you had 100% chance of reading that. That's what we're doing here. The setting of the theta is setting our probability because like we don't want just like random probabilities. Like we want to be able to like for a computer we want to program it. And so like with a quantum computer that means programming the probabilities. Yeah. And so changing this theta is like the manipulation that we need to do to actually program this like this machine.
And then so, sorry, I just wanted to clear. Does anyone have any questions about this? I know this is very heavier stuff, and this this process is a confusing one about how to encode this quantum information via the photon. Just any general questions that we could help clarify, because I know this is dense.
Believe it or not, makes sense so far.
It does not make sense?
It does.
Oh, okay.
It does?
Awesome.
Okay, cool.
So like what we're doing is we're composing this message, right? This one long message that is really 2 messages, except in random order, and also polarized differently based on if they were from the first message or from the second message. So for the first message, you always polarize 45 negative 45. And like it's either 45 or negative 45, right? But like the actual value, like you have 45 and negative 45, but one of them has to be a probability of 100% of realizing, right? And so like if it's a 1, then we put 45 to 100%. We adjust theta such that that amplitude is equal to whatever that squared would be to be 100% or 1. And so like the one thing to kind of like get is that the 45 negative 45 is always going to be for message 1. and the 090 is always going to be for message 2, right? And that might not make sense once I go through the receiving end. It might help clarify. So like, this is what it is: birefringent crystal, something that can depolarize light is what we need, right? And so what we're going to do is we're going to set this a certain way. We're going to set it either to say, hey, we want to do horizontal and vertical, and that's what we're going to measure, or we're going to do up diagonal, down diagonal, 45, negative 45, right? And the thing to understand here is that like the recipient knows that they can only receive one message. They know that the ordering, and the reason they know that is because the sender flipped a coin to determine what message to take from for the next bit. So like if we think about like having these like two messages, they're kind of scrambled together. And so our hope as a recipient is like, okay, this is like scrambled together. There's no way that we can get both of the messages. Like that's just like, we would have to accurately predict 100% of the sender's coin flips. And like, as the coin flips grows, that becomes like more unfeasible of a task, right? And so our choice then becomes, okay, well, like, fine, we can't get their coin flip correct all the time, but what if I just always measure a certain way and I'll always get from a certain message? That's the idea that like powers conjugate coding. It's this like inability to get both of the data, both of the streams of data accurately, because they're kind of like messed up, and you'd have to actually like predict the polarization scheme for every single coin flip. And since that is so unfeasible, you instead say, yeah, that sounds crazy. I'm just going to measure horizontal and vertical, and I'm going to receive the second message because that's what horizontal and vertical give me. And so like this, like important things to note is that like if the linear polarization is measured, which is the 0, 90, horizontal, vertical, we have absolutely no way of measuring the circular polarization, which is the 45, negative 45. And like that might seem like a hefty claim, but the reason that we can kind of like talk like this is because it kind of goes back to the measurement principle. If we have a quantum state that is like this really awesome composition of a whole ton of other funky states, just like Schrodinger's cat, when we open that box, we are measuring and collapsing that state onto a single classical value. And so if we had this photon that is traveling with two different components, with a horizontal vertical and a up diagonal and a right diagonal, well, taking that apart, measuring that in either way, there's no way to put that back together. There's no way to revive the cat and say, okay, well, the cat's back to being alive and dead. Like, no, that we would have to reverse entropy in some way, which, like, according to the second law of thermodynamics, wouldn't be possible. And so, like, that is like a big part of why conjugate coding works. And like the kind of like responses from the center, the recipient, the only rational response is to measure in a consistent manner, because they know that measuring in both or trying to measure both would give them kind of exponentially decreasing probability of actually getting the correct answer as like the number of coin flips or length of the string grows. And if we tried to instead say like, okay, well, I'm not going to measure 0, 90 or 45, negative 45, I'm going to do something in between, you would just be getting gibberish. You wouldn't be getting anything interesting, because like these probabilities wouldn't be 1 and 0. Like the actual transmission of information is because we set this theta to 1 and to or in such a way that like horizontal is 1 and vertical is 0. And like that's really important, because if we didn't do that, then we would have like an increase in noise, and we would have a decrease in reliability of the actual message transcripted or transported. Like that's something that's super, super important, right? Because like if you think about sending a text message to your family member or like friend, if you had like a 70% chance of your phone actually transmitting the letter that you typed, for every letter that you typed, you would be like not considered a very literate individual, likely with all your misspellings. The like idea is that like, yeah, there's randomness, but that randomness only applies to trying to predict what method of polarization I'm going to use as a sender. And so as a receiver, like trying to guess that's crazy talk. Instead, I'm going to just do depolarize in a manner that I know that I can, at least for some of these bits, have 100% probability of measuring the right answer. And so like that is super important, and that is why if we set up some like weird mix of like, well, not like tilting at 45, but like maybe like 22.5 degrees, and like trying to measure like that, well, we would lose the property of having for some messages 100% probability of measuring the right answer. And so like as message size grows, more gibberish that we're reading, right? And this like last important point that I want to kind of like highlight is that upon measurement, we are destroying this quantum state. We don't get to talk about quantum anymore, at least within that respect. This like kind of wraps up what conjugate coding is. It's not very like intuitive as to like what this would be applied for, but it does lay some really important foundational work for quantum information as a whole. And like that work is namely the fact that like we can encode messages and we can encode them in such a way that actually reading those messages destroys the message. That comes back to this like measurement is equal to destroying quantum state. So like if we were to kind of like let's say put the entirety of a single message into this like superposed bit stream, well, if someone read that before the intended recipient would be sitting there with a depolarizing beam splitter wondering, when the hell am I going to get to depolarize something? Because it'll have been depolarized. Once like someone intercepted that message, it's no longer like feasible to reconstruct that same quantum state. And so if Will is sending me a message and he's superposing it and it's like got this really crazy secret that he wants to share with me, if Michelle reads it before I read it, I'm going to know, because I'm going to receive it and it's not going to look like superposed states. It's going to look like bits. It's going to look like classical ones and zeros because she already did the work of depolarizing. Yeah. And so this depolarizing is kind of like an action that is not invertible. We can't just unmeasure something, right? It's like the only measurement, the only operation in quantum computing that is not reversible. And so like that allows us to set up things or set up the fundamental foundation for things like quantum key distribution, and specifically the BB84 protocol, which we'll go over like in a future lecture, but it capitalizes on the idea that we want to know, me and Will want to know that we're the only ones that read this. And if I send it to him and someone else reads it before, he'll know. So we can throw that message away, or we can like just ignore it, because we at least have this property that under classical computing we would never have, which is that we can tell when someone measured something, because measuring is a destructive action. And like that's such an important part of quantum computing, the fact that like measuring is like this like slapping you back into reality and saying, hey, you crazy person, quit talking about quantum mechanics, that's gibberish, you're in a classical world, or at least they say. And so Actually, I just want to go back into that. It's not even at least they say, it's like that's what it seems like.
Yeah, but any questions regarding this? It is a cool concept. Definitely some real world implications that would be huge. Cryptography would be a lot different. Um, Messaging would be different. You would be able to tell whenever messages were interrupted, and think about how that could apply to a lot of intelligence agencies or even your Snapchat app. Yeah, cool concept though. Any questions?
It does assume, of course, that I can't receive your message and then simply re-encode the message with the same encoding that you used in the first place.
So that's that it does assume that, and the reason that it assumes that is because like we proposed a coin flipping mechanism, right? And so as this message length grows, you are exponentially decreasing, or your probability looks like 2 to the 0.5 probability of 2 to the 0.5 n, where n is message size. And so like as this increases, you have to guess their coin flip, the result of their coin flip for every single coin flip. And so like you could get most of them correct, but what if me and Will compared our output? That's kind of like the underlying thing behind BB84 is this like final step of comparing output and saying like, okay, this is what I got. Is this kind of what you received? Or really this is how I flipped my coins. Is this how you flipped your coins? And so like, yes, it does assume that. And for small message size or for predictable randomization algorithms, you can certainly kind of like exploit that vulnerability and
if you had a true source of randomness though, which may not exist, but I guess what I'm saying is as long as you were able to encode the message based on these coin flips in a random fashion, you would not be able to repeat it, which there are a lot of different methods of producing random coin flips. So as long as you didn't know the random algorithm I used to encode it, you could not reproduce it. And you can also constantly switch that up. But it wouldn't matter. Teddy wouldn't have to know since I'm communicating with Teddy, Teddy wouldn't have to know my random algorithm. Only the malicious person trying to intercept the message would have to note it, and that is like a very difficult task.
Yeah, exactly. Because like I as a recipient, I'm like, you know what? I'm not gonna try and like read this and then put it back together. Like that's hopeless. That I'm just gonna read one portion of it, and I'm gonna do that by doing horizontal and vertical, and I'm gonna make no attempt at reconstructing. Whereas an adversary would have to say like, no, I can't to just do one or the other. I gotta actually predict every single coin flip so that I can send it back on the wire and the recipient can think that nothing's wrong with it. Yep. And so like intercepting and reading is not a problem. Intercepting and reading undetected is something that like as message size grows and like as the algorithm is like fairly unpredictable enough, it becomes more infeasible.
Cool. Any questions, concerns, questions about anything else either too? Not pertaining to the learning labs, but just about anything really.
If not, then thank you guys so much. I thank you all so much for coming and listening to us spew about this stuff. If you ever feel like you have something that you want to kind of give a presentation on, or you just want to kind of learn more, become more involved as like a director or a researcher, anything, just reach out to any of us and we're happy to send you some resources to like meet with you and just talk about what you think. Absolutely anything. I mean, like we want this community to be as like as driven by the masses as it can. You know, we don't want like this like isolated group of directors and researchers that are like doing everything and making all the decisions. Like, this is a new community and we want you guys to help and have the opportunity to be kind of like founders and leaders in this,
Yeah.
in this
And,
new
and
thing.
anything you guys, anyone would like to range on the Discord, like that Discord is for the masses. If anyone wants to make their own meetings, do their own thing, you know, we understand that carving out 2 hours of a Monday or 1 hour of Monday or whatever can be difficult sometimes. So if you guys want to meet on your own or develop your own projects and whatnot, or even just meet up, or if you guys would like some more educational videos, any of that stuff, we would love constructive feedback on how to grow this club.
So I saw a quick question that I just want to address right before we call it a day. So is it possible for such transmission to halt the message or destroy the message if any eavesdropper tries to read the message? It is possible. If me and Will were to compare our outputs mid kind of receival, then like we could say, okay, you know what, I'm getting gibberish, like don't even worry about it, don't send anything. But like more common practice is for us to just at the very end compare our output and say, well, you know what, like this was compromised. We're actually not going to use this. And so like a lot of times you won't send the important information on the first iteration. You know, you'll send like something like a random key that you can compare and see, is anyone listening to us? And at that point that you know you have a secure channel, what you can also just do, which is what quantum key distribution kind of like does or aims to do, is like we send across that message, and it's just a random stream of bits. And if me and Will got the same stream of bits, well, hey, let's use that to encode some messages to actually use that as a key to a cipher. And let's create some ciphertext out of the actual sensitive information we want to send. And like that whole key distribution problem that exists within cryptography is addressed, at least theoretically, by like this new ability to detect, did someone see my key? Did someone like actually compromise the integrity of like the origin of my message, or the confidentiality rather of my message? But yes, again, thanks so much for tuning in. I hope to see everyone next week.
Yeah, thank you guys. Maybe doing a poker night soon via the Discord. We will see how that develops. And any constructive criticism or any ideas or anything like regards to that, feel free to reach out. Thank you guys so much.
Thank you for your time, guys.
Of course.